In the last video, we saw why similar words live together, and that is because we have the idea of semantic search, which helps to put words that are that are close together semantically. They have vectors that are close by, such that when we measure their cosine similarity, we can actually see whether they're in the same direction, opposite direction, or they have nothing in common. So, to take that further, we are talking about the formula that lets AI measure meaning. We've already talked about the formula in the other video for sure, but we are focusing a little bit more on the nuances of that formula. So to measure similarity, right? We saw in the last video that we could use Euclidean distance, which, well, it tells us the distance between the two vectors, the vectors that represent the words, because we don't humans don't understand humans understand words, but machines do not understand those words. So for machines to understand our words, we now have to assign vectors to the words or the sentences or even the tokens, as you may see in some context. So let's go ahead and look at that particular. So we saw Euclidean distance and of course cosine similarity, which gives better result because it shows direction, because direction is more important than magnitude in the context of AI. So let's see that. So the formula that lets AI measure meaning, right? Modern AI systems represent words, sentences, documents, images, products, and users as vectors. So once information rather is converted into vectors, AI can compare meanings using a simple mathematical formula. So as simple as this is, I mean, you must have come across this in your vector class. I mean, I have a playlist on vectors on this channel, where dealt with dot product, vector product, magnitude, and things like that, right? So cosine similarity, simple formula, but it's so powerful. So A dot B over magnitude of it and multiplied by magnitude of B. So imagine, if you have converted maybe a word or a sentence or so into a vector, so you can find the dot. So you're now comparing two words like that. So you do the dot product, you find the magnitude for each vector, and then do this math, and you go on. So this formula powers embeddings. Okay, it powers semantic search, it powers recommendation systems, it powers retrieval augmented generation, it powers vector databases, it powers similarity search and clustering. To understand why this formula is so important, we first need to understand vectors and dot products. Okay, in case you've not done vectors before, it's a very simple concept. It's not a big deal. So a vector is an ordered list of numbers. First of all, example, you have A to be 1, 2, 3, and B is 4, 5, 6. In AI, vectors are used to represent meaning. So because computers do not understand human words, but they understand numbers, and they understand numbers as vectors and arrays and things like that. For instance, you have cat to be 0 0.8, 0 0.2, 0 0.6, and kitten is 0 0.7, 0 0.3, 0 0.5. Now you can see that these two vectors, I mean, each dimension is close by for cat and kitten, whereas for cat, 0.1 is far away from each of them, 0.9 far away from each of them, and 0.2 far away from each of them. So it could be like, and these dimensions now could be whatever. It could be that you're looking at them in terms of being animals or pets and things like that. Or maybe one is a child of the other, that kind of thing. So the offspring of the other, right? So the numbers themselves do not have obvious human interpretations. Instead, they are learned representations that place similar concepts near one another in a high dimensional space. So it's more like when people tell you that they trained they trained their model on some kind of data, right? So it means that the model reads through the tons of text and sees that, oh, based on probability, there's every chance that when you see cat, you see kitten close by and things like that. And when you see cat, the car is not always that close by, right? So it's so it is the algorithm, the machine learning from the tons of text they are fed, and to then now place all these things on probability that if you see this word, there's every likelihood that this word is going to be around it, that kind of thing. So the numbers themselves do not have obvious human interpretations. Instead, they are learned representations that place similar concepts near one another in a high dimensional space. So the challenge is, how do we measure similarity between vectors? Okay, so of course we saw that in the last video, right? We saw we could use Euclidean distance, and we can use cosine similarity. But here, even right there, we saw that cosine similarity is more important than Euclidean distance, because Euclidean distance shows magnitude, while cosine similarity shows direction. So, for instance, if cosine similarity is one, it means that the words are in the same direction. If it shows similarity zero, it means the words have nothing in common. If it shows similarity minus one, it means the words are in opposite directions. So the dot product combines. So the dot product now, that A dot B, it combines two vectors in a single number. So for vectors A is A1, A2, AN, and vector B is B1, B2 up to BN. The dot product is simply A dot B, which is A1 times B1 plus A2 times B2 plus all of that plus AN times BN. So the dot product measures how much two vectors point in the same direction. Example, so you have A is 1, 2, 3, and B is 4, 5, 6. So A dot B will be 1 times 4 plus 2 times 5 plus 3 times 6. That's 4 plus 10 plus 18, which is 32. So the dot product of 1, 2, 3, and 4, 5, 6 is simply 32. So if you do that using Python, of course, you can get that. So dot product is np dot A comma B, and that will also give you the dot product of 32. Of course, the programming part comes in when you are dealing with very large vectors, so you don't have to keep bothering yourself. So the code just does it for you. So now, geometric interpretation of the dot product. Now the dot product also has a geometric meaning, right? So for two vectors A and B, so the dot product is magnitude of A multiplied by magnitude of B multiplied by the cosine of the angle between the two vectors, and that is where the idea of so this cos theta now is what is called the cosine similarity, right? So cos theta now is A dot B over this. So where A is the length or magnitude of vector A, modulus B, modulus A is the length of magnitude of vector A, modulus B is the length of magnitude of vector B. Theta is the angle between the two vectors. So this equation is one of the most important equations in machine learning and AI. All right. So it's one of the most important. Now, we then go ahead to talk about vector magnitude. So the magnitude of a vector measures its strength for a vector, right? A is x comma y. So the magnitude is square root of x squared plus y squared. So for an n-dimensional vector, you then have modulus of A to be square root of A1 squared plus A2 squared plus AN squared, and so on and so forth. So the magnitude of a vector measures its length like that. So what's the magnitude of vector A, which is 3 comma 4? That's square root of 3 squared plus 4 squared, which is 9 plus 16, square root of 25, and that's 5. So the magnitude of the vector A 3 comma 4 is simply 5. So if you use Python code for that also, you declare the array, then you get num from linear algebra. So num is the same thing as uh magnitude in this case. Now, how do we derive cosine similarity? We already saw the formula, starting from the fact that dot product is modulus A modulus B cos theta. If you divide both sides by modulus A modulus B, you then get cos theta to be A dot B all over modulus A multiplied by modulus B. So this quantity is called a cosine similarity. That's how simply you derive that. So talking about the cosine similarity itself now, the cosine similarity between vectors A and B is this A dot B over magnitude A magnitude B. So cosine similarity measures how similar the directions of two vectors are. So the result lies between this. Minus 1 is less than or equal to the cosine similarity, and that is less than or equal to 1. So cosine similarity ranges from minus 1 to 1. So if you have 1, it means that the vectors are in the same direction. If your answer is 0, it means that the vectors are perpendicular. They have nothing in common. If it's minus 1, you have the vectors in opposite direction like that. So cosine similarity lies between minus 1 and 1. So imagine the cosine similarity of A is 1, 2, and B is 2, 3. Now, one thing we saw in the other video is that if either vector is a mag is a what is it called now? If one vector is a multiple of the other, then they are in the same direction perfectly. So to compute the dot product. I mean, and they have the same sign. I think I have to put that caveat. All right. So compute the dot product A dot B. That's 1, 2, 2, 3. That's 2 plus 6, which is 8. Then compute the magnitude. Oh, I did exactly this in the last video. So you have square root of 1 squared plus 2 squared, which is root 5. Square root of 2 squared plus 3 squared, that's root 13. So if you compute the cosine similarity, that's 8 over square root of 5 square root of 13. That's 8 over root 65, which is 8.0623. So if you put all that 8 over this now, you get 0.9923. So the vectors are highly similar. That's what this tells you. So it means that the vectors are in the same direction. So you can, of course, still do the Python code. So you declare vector A as 1, 2, np dot array 1, 2, np dot array 2, 3. So here you're simply converting a yeah, you're converting a list into into an array, something like that. And then the similarity, you define the formula dot the np dot, that's dot is coming from numpy, so dot ab divided by from the norm of a multiplied by the norm of b. So but norm is a function inside of the linear algebra module from numpy. So and you get those and you get your similarity, and the answer just shows up here. So now the question is, why not use Euclidean distance? We already saw the reason for that in the last video. So if you consider 1, 1 and 10, 10 as two different vectors, the Euclidean distance will be telling you they are 2.73 units apart. So this suggests the vectors are far apart. However, you see that B is 10A, B is simply 10 times vector A. So which means they point in exactly the same direction. So if you do the cosine similarity for this, you discover that the answer is 1. Therefore, cosine similarity captures directional similarity rather than absolute magnitude. And what matters more here is not magnitude, it is actually the direction in which they point. No matter how far apart they are, they're more interested in the directions they are facing. So, talking about embeddings, which we've talked about, I mean, in most of the videos so far in this playlist, an embedding is a vector representation learned by a neural network. Example, the cat sat on the mat. So, embeddings typically have hundreds of thousands of dimensions. So, examples of embeddings include things, you have different models for embedding, like word to vector, that's word to vector. It has 300 dimensions. You have globe 300 dimensions, BERT based 768 dimensions, modern LLM embeddings, which is like 1000 plus dimensions. Now, question, why embeddings capture meaning? Neural networks learn embeddings by observing patterns in large data sets. And that's why you don't sit down and start assigning vectors to words, right? But you basically train your model on some data, and then from the data, maybe from text or whatever. So from the data, they learn how things fit together, and then they assign the vectors to the words or tokens or sentences based on by assigning some probability, right? So words that appear in similar context receive similar vectors. So imagine examples like cat, kitten, felon, and dog. They tend to cluster together because I mean they have similarities. Then similarly, car, truck, bus, and engine form another cluster. As a result, semantic similarity becomes geometric proximity. So because these words are close together, they are going to have their vectors are really going to be pretty close, just like for cat, kitten, felon, and dog. So coming to measuring semantic similarity, then suppose we have embeddings like cat 0.8, 0.2, 0.6, and kitten 0.7, 0.3, 0.5, and cat 0.1, 0.9, 0.2. So you can already, by just inspection, right, you see that cat and kitten are close by in the different dimensions. So cosine similarity can then determine which concepts are semantically closer, and higher cosine similarity indicates more similar meanings. So if you find cosine similarities between cat and kitten, cat and car, kitten and car, you discover that cat and kitten will tend to be closest of the pairs. So imagine if you run this here now, so you put all the cards, all the arrays like that, and then you define a function, a cosine similarity AB, and you return dot product AB over the norms like this. So np dot linear dot norm of A. So then print cat versus kitten. So cosine similarity, cat kitten, cosine similarity, cat car. So for cat kitten, you have 0.99. For cat and car, that's 0.40. So that means 0.99 is tells you that cat and kitten are perfectly in the same direction, while cat and car are a bit far away. So, and we go on to talk about semantic search, which we've been talking about forever. So, traditional search relies on exact word matching. So, traditionally, right? So, if you query for car, the system is looking for car, but semantic search deals more about the meaning than the exactness of the word. So if you query automobile, for instance, and you have a document that contains car repair guide, I mean, there's no one-to-one matching of the words from your query and the document. But semantically, automobile, refers to car, and car can be repaired, and there can be a guide to do that repair. So here you see that keyword matching may fail because there are no keywords matching, but embedding search converts both query and document into vectors. So automobile is converted into a vector, car and repair guide, the document containing car repair guide is also converted into a vector. And because semantically they have the same meaning, so they will definitely be close together. So cosine similarity is then used to compare meanings rather than exact words. So meaning over word exactness, right? So meaning over keyword matching. So as a result, then you can see that automobile and car can be recognized as semantically similar. So then we talk about vector database, which we've mentioned before, but this is the first time we are dealing with it in this detail. So a vector database stores embeddings instead of plain text, right? So, you have you query, you put the words are broken down into tokens or words or sentences, and then the words are assigned vector dimensions, and then so those vectors are then stored into vector databases. So a vector database stores embeddings instead of plain text because machines do not understand words. We've said that several times. So each record contains, say, an ID, say 123, and you have the embeddings, the vectors, maybe all the 0.92, 0.52, and blah blah. And then the text assigned to that, which is how neural networks work. That might be your query or whatever. Then the database indexes vectors so your query is embedded, and the document upon which the AI algorithm you are using is also embedded, right? So that we can find similarities between them. So the database indexes vectors so that similar vectors can be found quickly. Instead of searching keywords, we search embeddings over keywords, right? Then we have similarity search in vector database. So given a query embedding, say Q, and document embeddings D1, D2 up to DN, the database computes cosine similarity between the query and each document. So that happens for each document. So documents with the highest similarity then scores, documents with the highest similarity scores are returned. For instance, you have this that neural network guides 0.95, deep learning tutorial 0.93, cooking recipe 0.11, right? So the first two documents are returned because they are semantically closest to the query. Uh, so the query is how neural networks work, right? So, and if you compare that with the documents, you discover that neural networks guide work better. It's closest to that query that was made, how neural networks work. So, deep learning tutorial, of course, a bit close, but not as close as neural network guides. And cooking recipes, a bit totally not so close. The first two documents are returned because they are semantically closest to the query. And then we talk about scalability, the scalability problem. Now, suppose the database contains 100 million vectors. So comparing the query against every vector requires, big O of N operations. This becomes computationally expensive at large scales. So vector databases therefore use specialized indexing techniques. So specialized indexing techniques help to reduce compute requirement. So, and that takes us to the idea of approximate nearest neighbor search. So, approximate nearest neighbor search algorithms avoid comparing against every vector. Instead, they efficiently locate vectors that are likely to be nearest neighbors. So, you have popular methods including HNSW, IVF, product quantization, PQ. Then you have scan The ANN methods provide faster search, lower memory usage, near optimal results, and this makes large-scale semantic search practical. And that is why, when you query AI, it can be so fast like that sometimes. Except if you now want to, so these days you can also set, depending on the level of thinking you want the AI to do. Then that takes us to the concept of retrieval augmented generation, which I've talked about in two or three previous videos already. So modern AI systems often use retrieval augmented generation, and the pipeline is like this. You have your user question or your query, which is embedded using a particular embedding model. Then you then have a vector search, so searching between your query and database, and then relevant documents, searching between your query and document, right? And then relevant documents are identified, and then you have large language models, and then the answers are generated, and voila, you have your results. So an example would be question: what is our company's refund policy? So steps, now you convert the question into an embedding. So because machine does not understand this English now, it's converting into vectors. So you then search a vector database, then you retrieve the most relevant document to whatever the embedding of this gives. Then you can send those documents to the large language model, and then that helps you to generate an informed answer. So examples of large language models include things like ChatGPT, Gemini, Notebook LM, I think, and so on. Then cosine similarity is the key retrieval mechanism in this case, so to generate an informed answer. In summary, we see that the entire semantic search ecosystem is built on one fundamental equation, simple equation. What the vectors we've been calculating forever, it's so simple. Cosine similarity, A dot B dot product over product of magnitude of the vectors involved. So, and the key ideas are as follows. Embeddings convert information into vectors. Dot products measure directional alignment. Magnitudes measure vector length. Cosine similarity measures angular similarity. Then similar meanings tend to produce similar vector directions. Vector databases store embeddings efficiently. Then ANN search finds nearest vectors quickly. Even when you have tons of information, ANN can quickly do that. Then RAG systems retrieve relevant knowledge using vector similarity. Now, without cosine similarity, embeddings will simply be large collections of numbers, you know, just large collection of numbers. So cosine similarity transforms those numbers into a measurable notion of meaning, right? So that's where it comes from. So the formula that lets AI, that lets AI have meaning, right? That's the formula that lets AI measure meaning. Yeah. So cosine similarity helps AI to measure meaning. Basically, that's the deal here. So cosine similarity helps AI to measure meaning. So cosine similarity transforms those numbers into a measurable notion of meaning. So let's see the practice problems. As usual, I get to solve two of them. So from here you can see questions 1 to 4. Compute the dot product of A and B. So that's easy peasy usually. And then you have 1 to 4 there. Then you have 5 to 8 like that. Then you have 9 to 10. In fact, you have 9 to 11 here. Then you can have 12. A query embedding has cosine similarities. This you have 12 there. Then with 5 documents, which two documents should be returned if the system retrieves the top two matches? Then so you have 12 to let's say 12 to okay, let's leave it at 12 to 15. You can see 12 to 15 very well here. Then so I'm solving question 10, by the way. So question 10, compute the cosine similarity between 111 202. Okay, that's simple. Then I'll be doing 10 and then I'll be doing 18. I'll be solving 18 also. So here we see le- okay, I think here we can see 16. Hope I've not skipped anything. So let's say 13 to 16 is clear here. Then 13 to 16, then 16 to the end. So I was taking care of 10, like I said, and 18. 18 talks about explain the role of embeddings in a retrieval augmented generation system. Retrieval augmented generation system. And the last one says write a Python function named cosine similarity AB that computes cosine similarity between two numpy vectors. I mean, we have that already done in the so all those cosine similarity things you saw, those are the kind of codes we are required to deal with. So things like this now. So let's go ahead and look at let's take care of the questions. Questions 10 and 18. So I start with problem 10. So for problem 10 now, so compute the cosine similarity between A, which is 1, 1, 1, and B, which is 202. Okay. So with this now, we just go ahead and do the solution. So straight up, we know that the similarity between A and B is computed by the dot product of AB all over the magnitude of A over the magnitude of B, or what you can call norm. So, and for A, right, it's like we have 1, 1, 1 dot 202. Interestingly, going up, uh, one very popular person in our environment had a car whose number was LA202BC. So we have fond memories of him as about 202. So yeah, we have 202 coming up here. So we have 111202. Then all over the magnitude, of course, magnitude of 111, then magnitude of 202 again. So, and for the dot product, right, you just multiply corresponding components and add together. So you have 1 multiplied by 2. So that's 1 times 2, 1, 2, plus 1 times 0, that's 1, 0, plus 1 times 2, this 1 and 2, all over the square root of 1 squared plus 1 squared plus 1 squared plus square root of 2 squared plus 0 squared plus 2 squared. So that then becomes 2 plus 0 plus 2 all over square root of, not so fast, so this square root of 111, that is root 3 multiplied by root 2 squared, that's 4 plus 4, that is 8, I think. Yeah, that's 8. So then that is 4 all over root 24. 4 over root 24. Now we can tidy that up as this. So that's 4 over 4 times 6. That is 2 roots 6 right there. And then we can rationalize. So we rationalize, we have, okay, I mean, this is just 2 over root 6, right? 2 over root 6, which we can rationalize as 2 over root 6 times root 6 over root 6. So that is 2 root 6 all over 6. And then 2 root 6 over 6, that's root 6 over 3, because 2 goes here, 1, 2 goes here 3 times. And that is, so the similarity between A comma B is then approximately the same thing as 0.8165. So here now we see that the vectors are fairly similar. The vectors are fairly similar because the cosine similarity is close to 1. Okay, so that's about question 10. So we'll move on to question 18. That's problem 18 now. So explain the role of embeddings in a retrieval-augmented generation system. Explain the role of embeddings in a retrieval-augmented generation, RAG system. Okay, so we go step by step there. Step 1, convert documents into embeddings, right? So step 1, convert documents into embeddings. Okay, so let's say that, suppose a company has documents. Okay, suppose a company has the following documents, right? Refund policy, refund policy, employee handbook, product manual. So each document is converted into a vector database, Each document is converted into a vector, right? Each document is converted into a vector, D1, D2, D3, all right? So then these vectors are stored in a vector database. They're stored in a vector database. So that's step one there. So for step two, the next thing is convert the user query into an embedding. So imagine the user asks, how long do customers have to request a refund? That's a user query right there. So the embedding model converts the question into a vector, converts the question into a vector like that. And then the next thing is to compare query and documents. So step three, compare query and documents. So the system computes cosine similarity QDI for every document vector. So example, you have document, I have similarity. So for refund policy, you have 0.97. For employee handbook, 0.21. Product manual, 0.34. So that's step three now. So you compare query and documents. So don't forget, how long do customers have to request a refund? So refund policy, see, that has the highest score, followed by product manual 0.34 and employee handbook 0.21. So you already have an idea what is going to be the most important. So for step four, you then talk about retrieving. So you retrieve relevant documents. So the document, with the highest similarity score, is selected. So, and then that's a refund policy. So refund policy will just be selected. I mean, this is just a skeletal idea of what really happens, right? So because 0.97 is the largest similarity value. Similarity value. Okay, so that's step 4 there. So gradually drawing to a close, then we have step 5. So for step 5, we then send retrieved information to LLM. So the retrieved text is added to the prompt, sent to the language model. So generally, you then have something like a question plus relevant documents. Okay. So questions plus relevant documents, right? Leading to LLM and then leading to answer. And then you have that whole thing. Like that. So in essence, we have this as final answer. Embeddings are the foundation. Embeddings are the foundation of RAG because they transform both documents and user queries into vectors. So these vectors, okay, I guess I want to change here. Okay, I thought I had these vectors make it possible to use cosine similarity to retrieve the most semantically relevant documents from a vector database before the LLM generates an answer. Yeah, so queries from users are embedded, as well as as well as relevant information in documents are also embedded so that there can be easy matching. All right, so with this, we come to the end of this interesting video about the formula that lets AI measure meaning, which is cosine similarity easily. Okay, so again, look at the questions. You have questions 1 to 4 clearly displayed there. Questions 1 to 4. 1 to 4, all of them displayed. Then 5, 5 to 5 to 8 clearly displayed here. Then 9 to, okay, say 9 to 11. We have 9 to 11 here. We have 12 to 16. 12 to 16 fully displayed. Then 17 to 20. So let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't, why not go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join, right? So when you click on join, you find, uh, you know, you'll find some very special benefits that you get as a member of the channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.